Hello students, welcome to the class. So in the previous class, we have discussed regarding modern periodic law, distribution of the elements in different forms we have seen. In the first form, we have seen how the elements are distributed in the periodic table in the form of groups and periods, and we know what are periods and groups. The 18 vertical columns are called groups. Speciality of the group is that whatever elements come in a group, since they have same valential electronic configuration, they exhibit similar properties. Periods, there are seven horizontal rows and those are called periods, and the speciality is that every period starts with a alkali metal and ends with a noble gas. Yes. So if you are asked to explain what are the merits of the modern periodic table, you can say it is quite easy to remember and reproduce. Modern periodic table, as we have seen here, it is quite easy to remember and reproduce. The position of the elements in the periodic table, they are linked with what? They are linked with the atomic, their electronic configuration. Therefore, I can say they are linked with the atomic number as the rule says, as the law says. Each group is an independent group. So if you look at the groups, group 1 to 18, we know each group is independent. It is not dependent on any other group, or like how Mendeleev had given that there are subgroups. Like that, there were no subgroups here. So idea of subgroups, as in case of Mendeleev's periodic table, it has been discarded. It is not followed. There is one position for all the elements, isotopes of the elements, because isotopes have got same atomic numbers. Yes. So example, three isotopes of hydrogen. Which are those? Protium, deuterium, tritium. They have different what? They have different atomic masses, but the atomic number is one only. Therefore, all the isotopes of a particular element, they are being placed under same block. Yes. This periodic table, it is linked with what? It is linked with the electronic configuration. Hence, so it is linked with the electronic configuration. Hence, the further division of the elements into S, P, D and F blocks has been quite useful in understanding the properties. But there are few limitations also. The limitations coming to, in the, if you see the periodic table, position of hydrogen is still a question. It is still uncertain. Still the question is there whether it has to be placed in group 1 or group 2. If you are seeing in this particular picture what I have shown, hydrogen is placed in group 1, but it is not a group 1 element. Yes, to avoid the questions that is placed there, actually hydrogen will be placed at the center. Yeah. And inner transition elements, which are inner transition elements? D, F block elements. They do not find a place in the main body of the table, so only it is being placed at the bottom. They are placed separately below the periodic table. Yes. So we have seen, apart from periods and groups, they have been divided into blocks also. S block comprises of two groups, group 1 and group 2. P block comprises of 6 groups, group 13, 14, 15, 16, 17 and 18. D block comprises of 10 groups from 3 to 12, and F block comprises of 14 groups, which are placed at the bottom. They are called lanthanides and actinides. Yeah. Apart from this also, the periodic table is being classified as metals, non-metals and metalloids. We know it. Yes. What do we know? We know that the elements, yes, elements are the pure substances, right? These are being classified into three types. What are they? They are metals, non-metals and metalloids. Yes. These metalloids are also called as semi-metals. Okay. So based on what characteristics are these being classified? Depending upon the physical properties, you can say. Physical properties, the elements are being classified as metals, non-metals and metalloids into the periodic table. Okay, metals comprise more than 78% of all the known elements. So maximum are metals, then they appear on the left side of the periodic table. Metals are solids at room temperature. Yes, it exists in solid state. The only metal which is liquid at room temperature is what? It is mercury. So only metal which is liquid at room temperature. Metals usually have high melting and boiling points. Metals are very hard. Yes, they are very hard. But there are few metals like sodium, potassium. These are soft. So soft that they can even be cut with knife. You can even cut it with a knife. So usually metals are hard, but certain metals like sodium, potassium, they are soft and even be cut with a knife. They are good conductors of heat and electricity. Yes, the best conductor of heat and electricity is silver. So only they are called conductors. They conduct heat and electricity. They are malleable and ductile. That means what? When you hit the metal, if you take a certain metal, when you hit it, yes, you get it into thin sheets. Yes, suppose I have a block of metal. Yes, say I have block of metal, I will hammer it, I will apply pressure on it. Yes, so when I apply pressure on it, it becomes a thin sheet. That property is called malleability. I've studied it in your lower classes also. It is called malleability. And most malleable is gold. Most valuable is gold, silver, and so on. Second one, if you take a metal, you heat it and pull it on both the ends. Yes, it comes into long wires. That property is called ductility. It is called ductility. And the most ductile is also gold and silver. Most ductile metals. Yes. Metals. Next property is that metals are electropositive in nature. Please do remember this point. This point comes under chemical behavior. Electropositivity. That means metals have the tendency to lose electrons, one or more electrons. They have the tendency to lose one or more electrons. The reason is the atoms present in the metal, they have got they have got large atomic size. So the electron is of the outermost, always the outermost electron will be removed. So this is far away from the nucleus. So nuclear attraction is quite less. I cannot say it is completely zero. It is quite less. So you can remove this electron very easily. So all the metals, they are electropositive in nature. They tend to lose electrons. And most electropositive metal is cesium. Cesium. Its value of electronegativity, it is, or you can say it is least electronegative. Yes, and that its value is 0.7. Yes, so this is chemical property of metals. Metals are sonorous and lustrous. That means when you hit a metal, they produce a ringing sound. Not just a sound, they produce a ringing sound which echoes. Lustrous, they have shiny surface. But if you see these metals, when suppose I take a block of sodium, yes, it is having lustrous surface, yes, shiny surface. But after some time, this shiny surface disappears. The reason is, as soon as you get the metal to atmosphere, it will react with oxygen and form a layer of oxide, which covers the metal. Therefore, the shiny surface disappears. You again scrap out the layer, or may use any method to remove that layer of oxide. Again, it will have a shiny surface. So we say metals are sonorous and they are lustrous. Last point, they are electropositive in nature. They tend to lose electrons very easily. They tend to lose electrons very easily. And examples of metals you all know only. Yes, sodium, lithium, potassium, calcium, beryllium, magnesium, aluminium. Yes, copper, iron, nickel, cobalt, zinc. All these are examples of metals. Non-metals. Non-metals are located at the top right hand side of the periodic table. Excuse me. Non-metals are usually solids or they are gases at low temperature with low melting and boiling points. But there is a non-metal which is also liquid at room temperature. The non-metal which is liquid at room temperature is bromine. Bromine is the non-metal which is liquid at room temperature. Okay, otherwise they are solids or gases. Boron is a non-metal, carbon is a non-metal. These are all solids. Gases, if you see, nitrogen, oxygen, fluorine, iodine is solid. Then chlorine we have. Bromine is liquid. The only non-metal which is liquid at room temperature is bromine. They are poor conductors of heat and electricity. They do not have the tendency to conduct heat and electricity. Therefore, they are called insulators, whereas metals are called conductors and these are called insulators. The non-metallic character increases as we go from left to right in the periodic table. The most non-metals are solid, Most non-metallic solids are brittle. That means when you hit a non-metal, like how unlike metals, when you hit it, you can get it into thin sheets or you can bring them into long wires. But it is not in case of non-metals. They are brittle. When you hit or apply pressure to it, they become into pieces. And still more pressure you apply, you get it in powdered form. Yes, so they are neither malleable nor ductile. Instead, they are brittle. As I said, non-metals are poor conductors of heat and electricity with some exception. The exception is that the allotropic form of carbon, that is graphite, this is the only exception. It conducts electricity. It conducts electricity. So this is the exception. Okay. So these are the properties. On the other hand, non-metals are electronegative in nature. They are electronegative in nature. So electronegative means what? Electronegativity. Metals are electropositive. Non-metals are electronegative. So non-metals, they are electronegative. Actual definition of electronegativity is tendency to attract the shared pair. But you just remember, non-metals have the capacity to gain electrons easily because they have got smaller atomic size. Their atomic size is very small. Therefore, what happens if any electron is in the vicinity, it will immediately gain. So metals, they are electropositive. So electropositive means what? They tend to lose electrons. Yes. So metals lose electrons and become positive ions. Electron comes out. Those positive ions are called cations. Non-metals gain electrons easily and they form negative ions. And those negative ions are called anions. So ions are what? They are the species formed by loss or gain of electrons. Cations are formed by metals, anions are formed by non-metals. And depending upon how many electrons are lost, the cation charge goes on changing. So monovalent cation is +1, loss of 1 electron. Bivalent is +2. Similarly, monovalent anion -1. So you have examples here. Na is plus, whereas Mg is +2. Then potassium is plus, calcium is +2. So these are metals. In case of non-metals, F is minus, O is -2. Yes, or you can say Cl minus, sulfide -2. So they form ions. They form ions. Yes. So these are the properties of metals and non-metals. Metalloids. Few elements like silicon, germanium, arsenic, antimony, tellurium in the periodic table, they show characteristics of both metals and non-metals. And these elements are called metalloids, or you can call them semi-metals. So if you look at the periodic table, you can see here at the left side are metals. In the center of the periodic table are also metals. Then here also at the bottom are also metals. So these are metals at the bottom. And here, these are non-metals. These also are metals. So maximum are metals. Then here, can you say this? Silicon, germanium, arsenic, these are what? Metalloids. These are metalloids. These are said is separately halogens. These are noble gases. So I can say, so where metals are present? Metals at the left side of the periodic table, at the middle, I'm sorry, rather than say center, at the middle of the periodic table, and at the right side, right bottom side. Yes or no? Right bottom side are the metals. So can I say metallic character is more here, metallic character is less here? So with this explanation, can I say that metallic character, as you move from left to right, from left to right, where? In periodic table. Yes, when I say left to right, it is like this. So metallic character, what happens from left to right? It decreases. So metallic character from left to right decreases. Yes. Then metallic character from top to bottom. So just now I said at the bottom part there are metals, right? In periodic table. I mean from top to bottom. What happens to the metallic character? It increases. And vice versa is for non-metallic. So here I can say non-metallic character. What happens to the non-metallic character from left to right? It increases because metallic character is decreasing. And non-metallic character from top to bottom, what happens? It decreases. It decreases. Is that right? So metallic character, as you move from left to right in the periodic table, metallic character decreases. And as you move from top to bottom in the periodic table, metallic character increases. Non-metallic, when you move from left to right, here there are more non-metals, so non-metallic character increases. Whereas top to bottom, non-metallic character decreases. Is that clear? Yes. So here are metals, strong metals, and here are non-metals. Yes. So fluorine is most electronegative. Most electronegative. See, Pauling, there was a scientist by name Pauling. He had given a scale for electronegativity. Electronegativity has got no unit, but there is a scale starting from 0.7 to 4. So 4 is most electronegative. Yes, I'll write it here. So electronegativity scale was given by Ehrlich Pauling. So E. Pauling. So the scale varies from 0.7 to 4. Yes. 4 means what? Most electronegative. 0.7 means least electronegative. Least electronegative is cesium. Most electronegative is fluorine. So fluorine electronegativity value is 4. The next most electronegative is oxygen with electronegativity value 3.5. Then comes chlorine 3.3. So these are most electronegative elements. Most electronegative elements. Right? So this is about metals, non-metals and metalloids. They have properties of both metals and non-metals, we say. What does that mean? We know that metals are called conductors. So they conduct, I'm giving simple example. They conduct electricity. Whereas non-metals are called what? Insulators. They are poor conductors of electricity. They do not conduct electricity. These metalloids under normal conditions, say example of silicon, under normal conditions, it does not conduct electricity. Does not conduct electricity. So it acts as insulators. Okay. But when the same silicon is heated or it is added with some impurity, some different compound you add, we call it as doping. When you dope it with some other element, it will conduct electricity. It behaves as conductors. So under normal conditions, it is insulator. It is behaving as a non-metal, and on heating or adding impurity is behaving like conductors. That is, it is behaving like metals. Therefore, these all metalloids are called semiconductors. They are called semiconductors. Best examples are your silicon, germanium, arsenic, antimony, then tellurium. These are the examples. Even polonium also comes. These are the examples of metalloids. These are the examples of metalloids. Noble gases. These are the elements present in group 18. Each period ends with a noble gas element. All the members are of gaseous nature, and because of the presence of all the occupied cell filled orbitals, they have very little tendency to take part in the chemical combination. See, if you look at the electronic configurations of all the noble gases, 1s2, neon, it is 10, 1s2, 2s2, 2p6. Yes, outermost shell, S should have 2 electrons maximum, it is having. P should have 6 electrons, it is having. So outermost shells are completely filled. Completely filled. So when it is completely filled, it becomes stable. unlike other elements. If you see all the other elements except these group 18 elements, remaining all elements do not have completely filled orbitals. Therefore, they are reactive. Yes, whereas group 18 elements, since they have completely filled orbitals, outermost shell, they are very stable. So since they are stable, they have got very low reactivity, very low chemical reactivity. That's the reason they are called as inert gases. They are called as inert gases. Understanding? So they are called as inert gases. Yes. So noble gases are called inert gases. But under certain very strong conditions of high temperature and pressures, an element of noble gas, xenon, it shows certain reactivity. Hence the name noble gases. So it shows certain noble behavior. Therefore, they are called noble gases. And these inert gases or noble gases are also called rare gases because in the atmosphere, their percentage of appearance is very less. Out of all these noble gases, helium, neon, argon, krypton, xenon, and radon, these are all very, very trace amounts they are present. But the noble gas which is present in, compared to all of them, which is present in more amounts is argon. So it is present in abundance, we can say. Yes, or they are called zero group elements. Why they are called zero group elements, that I'll be discussing in the next topic where we come across octet configuration. They are called zero group elements. Okay. So these are also called inert gases. They are also called inert gases. Next, we have representative elements. When I was discussing S block elements, P block elements, I have already told you. Group 1, Group 2, Group 13 to Group 17. Group 1 and 2 of S block, Group 13 to 17 of P block. These elements, they are called representative elements. They are called normal elements. Yes. Why they constitute representative elements? Or why they are called normal elements? Because the elements of group 1 and group 2 and group 13 to 17, they are most frequently used elements and they are quite reactive elements. They form lot many compounds. That's the reason they are called representative elements. They are said to be representative elements, right? Transition elements. So what do we mean by transition elements? The elements include all the D block elements and they are present in the center of the periodic table. Yes, when I was explaining about D block, I have told you the general configuration of D block is noble gas configuration NS1 or 2 or 0 to 2 and N minus 1D 1 to 14. So the last electron, or what we call it as the differentiating electron, it enters into not the last shell, but it enters into N minus 1th shell. That is the penultimate shell. Penultimate shell. Therefore, they are called as transition elements. They are called as transition elements. This is one reason why they are called as transition. The second reason is, I can show you all here, when you are seeing the periodic table, there is a transition. So in at the left side, there are metals. As you move in the periodic table from left to right, there are non-metals, right? So when you are moving across in the D block elements, which are placed at the center, when you move from the beginning, that is from group number 3, as you proceed to group number 12, there is decrease in the metallic character, or you can say there is increase in the non-metallic character. So there is transition shown. I can give you an example how to say decrease in metallic character. The elements in the beginning, scandium, titanium, they all iron, they all form ionic compounds. They all form ionic compounds. But when you see at the last, zinc and all, they form covalent compounds. So formation of ionic compounds is the characteristics of a metal. Covalent compounds, it is the characteristics of the non-metal. So there is a transition between from metals to non-metals. That's the reason they are called transition elements, or you can call them as transition metals. So all of them are transition metals. Yes. Okay. Inner transition metals, lanthanides and actinoids. Lanthanides, they are starting from what? They are starting from 58 cerium to 71 lutetium, 14 elements. 14 elements, and actinoids starting from 90 thorium to 103 lawrencium. Yes, these are also 14 elements. They are called inner transition elements. The reason is they belong to F block. When you see F block, it is noble gas core configuration, NS 2, n minus 1d 0 to 2 we have seen, then n minus 2f 1 to 14. That means the differentiating electron is entering where? It is entering into n minus 2th shell, and this n minus 2 shell is called anti-penultimate shell. It is called anti-penultimate shell. That's the reason, and they are present within transition elements. They are present within transition elements. Therefore, they are called inner transition elements. And the elements after uranium, they are also called transuranic elements. That means they have behavior of uranium, so they are called transuranic elements. Examples for, if you look at the periodic table, examples for transuranic elements are neptunium, plutonium you have, then americium, californium, berkelium. Yes, these are all called transuranic elements which are present in actinoids. Okay. Now see, there were all, when the modern periodic law or modern periodic table was given, all of the 118 elements were not discovered. Yes, rather last few elements are discovered in the last few years. So nomenclature of the elements with atomic number above 100. See, today we know the nomenclature of the elements we have seen. Yes, how the elements are being named. We see, if you take example of, there are rules for naming the elements, right? We write symbols also for the elements, right? But after 100 elements, there was a question. After 100 elements, there was a question, because when the elements, as per the modern periodic table, there are 118 elements that are known to a man today, out of which 24 are synthetically prepared. Those which were obtained into the nature, they were all naturally obtained. Remaining 24 elements, they are artificially prepared, while the rest are naturally occurring. Some of these elements were discovered much before, and other elements have been discovered recently by a team headed by Glenn Seaborg and Lawrence Berkeley Laboratory in Berkeley, California. Many of these elements have been assigned their names and symbols. Like, for example, if you see the example of, say, Einsteinium. Yes, example, atomic number 99. Yes, it is Einsteinium. So Einstein had discovered it, so he gave it his name. Then we have one more example like mercurium. Sorry, not mercurium. Curium. Curium we have. It was discovered by Madame Curie. Yes. So like that, they were given their names and symbols. But still, these symbols and names are not used universally. Some of the two names and symbols are given. You can see here, for example, the discovery of an element having atomic number 104, it was claimed. See, the 104 element, the element 104, it was discovered, it was claimed that Americans also had discovered it, and Soviet scientists also had discovered it. So there were, I cannot say always an element will be discovered by only one person. 10 of them can discover one element. Yes. So Americans, what they did, Americans gave it the name as Rutherfordium. Atomic number 104 is Rutherfordium. Yes, it is called Rutherford. They gave the name as Rutherfordium and gave the symbol as RF. Whereas Soviet people, they assigned the name as Kurchatovium and gave the symbol as Ku. So which one to use? When other part of the world has to use this element, whether they have to use RF or Ku. In the same way, another element having atomic number 107, it was named as Niels Bohrium as well as Bohrium. So Niels Bohrium NS, Bohrium BH. Which one to use? Looking at them only, we feel they are both two different elements. Therefore, to eliminate all these issues, and there was a fight between at least Rutherfordium and Kurchatovium, there was a big fight. Americans were saying it is Rutherfordium only because we have discovered it. Soviet scientists were saying it was Kurchatovium because we have discovered it. So to eliminate all these issues, IUPAC, International Union of Pure and Applied Chemistry, it made a commission of nomenclature in inorganic chemistry. So commission of nomenclature in inorganic chemistry to assign clear system of nomenclature for the elements having atomic numbers greater than 40. Yes, and those elements were also known as super heavy elements. So what are super heavy elements? The elements whose atomic number is more than 100, they were called super heavy elements. And IUPAC committee, it made a commission, CNIC, So Commission of Nomenclature for Inorganic Chemistry. Yes. So they gave certain rules. After having a discussion with scientists all over the world, in 1997, the IUPAC decided the official names for the elements with atomic number 104 to 110 and recommended a system for nomenclature of these elements. They gave a system. Yes, it's simple. Like, try to understand. When a baby is born, what we do, as soon as the baby is born, we try to give so many different, try to call it by so many nicknames, right? Whatever we feel, we try to call it. But after certain days, we give official namkarana, we do, right? For the baby's naming ceremony, we carry out and give a typical name, which is being followed in all his documentations and everything. Similarly, as soon as the element is discovered, what people, scientists try to do, they try to give their names and the symbols. But it has to be recommended by IUPAC. Only if you give 100% explanation for the element which you have discovered, then it will be named after that particular scientist. Otherwise, till the discovery is proven, you have to follow the name which is given by IUPAC for the 100 and elements with atomic number greater than 100. So what was the rule? The rule was very simple. Yes, suppose they said the naming of the element. So what they said is you have to give notations. You have to give notations. And these notations were derived from the atomic numbers only. Atomic numbers only. For example, what they said is atomic numbers contain Arabic numerals like 100, 110, 105, right? So they gave certain root words for these numerals. So they gave, for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 0 to 9, what they gave the root words. So you have to use these root words, combine all of them, and form the atomic form the name of IUPAC name of the element. For example, the root word for 0 was nil. For 1, it was un. For 2, it was bi. For 3, it was tri. For 4, it was quad. Yes, we say no quadrilaterals. For 5, it was pent. For 6, it was hex. For 7, it was sept. For 8, it was oct. And for 9, it was n. And there were symbols also. So nil, n starting. Here, U, B, T, Q, P, hex, sept, oct, n. Right? So these were the formats used. These were all notations being used. So if you have an atomic number if you have an element with atomic number 101, so how do you follow? You follow these numbers only. So 1 means what? Un. Plus 0 means what? Nil. Plus 1 means what? Un. And followed by, you have to add the suffix I, U, M. So what will be the name? Un, nil, un, I, U, M. And if you want the symbol, use the first letters. Finish. 3 letters. U, N, U. So this is the symbol for the element. 110. If I want 110. Un, nil, I, U, M. So un, nil. So U, U, N. If it is 114. Un, quad. IUM. I have to put the suffix IUM. So unquad. So U, U, Q. Understanding? If it is 108, I'm sorry, nil, oct, IUM. So nil, oct, UNO. Understanding? 109, nil, NIUM. So UNE. So this was the symbol and this was the official name for the elements with atomic numbers greater than 100. Yes, greater than 100. So important points of this nomenclature system for the elements with atomic number more than 100 are: the names can directly be written from atomic numbers by writing numerical roots of required numbers from 0 to 9, and then by adding the suffix IUM. A mixture of Latin and Greek roots is used so that there is no duplicity in the symbol. Yes. In some cases, the names are minimized. For example, by Yes, suppose the element is 1, 1, 2. So what I'll do, un, by, I should write, correct? So there is 2 times I coming. So you can minimize it. Yes. And you can write it as un remains as it is. By double time I can be written as bium. That's it. But the symbol remains UUB. Yes, so it can be reduced also. The symbol of an element can be given by writing the roots of all the numbers in atomic number of the element and adding the suffix ium. Yes, so this is, see, you can see here the root words: 0, nil, n; 1, un, u; 2, bi, b; 3, tri, t; 4, quad, q; 5, pent, p; 6, hex, h; 7, sept, s; 8, oct, o; 9, n, e. So these were the root words and the symbols used. So here you have all the names you can see here. So 101, un, nil, un, ium, unu. Later it was proved, the discovery was being proved by Mendeleev. Therefore it was called Mendelevium, and later it was called 100 MD. 102. Similarly, un, nil, bium, unb. It was being given by Nobelium, no. 103. unt, trium, Lawrencium, lr. 104. unq, quadium, Rutherfordium. Rutherford gave the explanation for the discovery, so it is named after him. So RF is the symbol. So once the discovery is being proved, you don't have to use this. 105. un, nil, pentium, dubnium, db. 106, unnil hexium, seaborgium, Sg. 107, unnil septium, borium, it is called borium. 108, unnil octium, UNO, hafnium, Hs. 109, unnil ennium, UNE, metnerium, it is called MT. 110, Nillium, UUN, Darmstadium, DS. 111, Unnium, UUU, Ronchingium, it is called RG. 112, Coppercium, Unbium, Coppercium. After this, still the discovery, elements are discovered, but they are not being patented on any of the scientists or places. Therefore, they are placed as it is. So it is trium, quadium, pentrium, pentium, hexium, septium, octium. So this is about the IUPAC of a nomenclature, a systematic nomenclature before the official name is being given. Yes. Moving to the next one. Okay. Before this, as I said, the elements are being classified into blocks, right? Or they are being classified into groups and periods. Now, what if they give certain element and they will ask you to predict to which block it belongs, to which group it belongs, and to which period it belongs? What you need to do is you need to observe the electronic configuration. Observe the electronic configuration. The differentiating electron. So, if you want to say which block it belongs, the differentiating electron is entering into which orbital? That is the block. Third point, if you want to say period, to which period it belongs, it is nothing but maximum value of n. Maximum value of n is what? Of principal quantum number, that is shell number n. Which number is maximum, it will belong to that period. Fourth one, if you want to say to which group it belongs. Okay. If it is going to belong to S block, sorry, in S block, you can identify by number of valence electrons. Valence electrons. If there is one valence electron in the outermost shell, it belongs to group 1. Two valence electrons in the outermost shell, group 2. For P block, it is 10 plus number of valence electrons. So in the valence electron, if in the valence shell, if there are, say, and it should be p subshell, okay, so it is nsnp. So if it is one electron in p subshell, so they'll write 10 plus 1, that is Okay, so 2 and here 1. So it becomes 10 plus 3. It is 13th group. I'll show you the examples. For D block, it is Ns plus number of N minus 1D electrons. Ns plus N minus number of 1D electrons. F, you need not worry. Looking at the electronic configuration, you'll get to know. For example, suppose let me say I have calcium. I don't know to which block it belongs. So I'll write configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this is 10, this is 10. So it's 20. Okay. Now I want to speak about block. I want to speak about group. I want to speak about period. To which period it belongs. Okay. So how do I say it? Block. Last electron is entering into s orbital, therefore it belongs to s block. Period, which is the maximum number. This is 1, 2, 3, 4. So n is equal to 4. Therefore, I'll say it belongs to fourth period. Okay, group. Is it of S block? Yes. How many electrons? 2 electrons. Therefore, it belongs to second group. It belongs to second group. Example. Second example. Okay. I will take phosphorus. Atomic number is 15. Okay. 1s2, 2s2, 2p6, 3s2, 3p3. Correct? 10 plus 5, 15. Okay. To which block it belongs? Last electron is entering into p orbital, so it belongs to p block. So what is the period number? Which is a maximum number 3. So it belongs to third period. You can verify it. It belongs to third period. Group. So outermost shell is having how many electrons? 5 electrons, and it is belonging to p block. Therefore, 5 plus 10. It belongs to 15th group. That is nitrogen family. That is true. Third one. Let me take example of copper. 29. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d, 10. Correct? To which block it belongs? Last electron is entering to d orbital, therefore it belongs to d block. Period, which is the highest number? 1, 2, 3, and 4. So it belongs to fourth period. Correct? Belongs to fourth period. Group. It is of D block, right? So outermost shell is having how many? It is having 10 plus 1, 11 electrons. So it belongs to 11th group. You can verify it out and see. So this is how we predict the position of the elements in the period, in which block it belongs, to which period it belongs, and it belongs to which group. This is how we predict all these characters. Moving to the next one. Periodic trends in properties of elements. What are periodic trends? Periodic trends are specific patterns in the properties of the chemical elements that are revealed in the periodic table. Major periodic trends include what? Electronegativity, ionization energy, electron affinity, atomic radii, ionic radii, metallic character, chemical reactivity. So when do these periodic trends arise? Periodic trends arise from the changes in the atomic structure of the elements within their respective periods and even in the groups in the periodic table. So when there is change in the atomic structure means what? Electronic configuration, there will be different periodic trends. These laws enable the chemical elements to be organized in the periodic table based on their atomic structures and properties. Due to the periodic trends, the unknown properties of any element can be partially known. So because of these periodic trends, you can, even if there are some elements whose certain properties are unknown, you can predict the properties of those unknown elements. And that was what Mendeleev had did. He had predicted the property of the elements which were not discovered, Eka aluminum and Eka silicon. How? Based on the periodic trends in the periodic table. Several exceptions also exist. We cannot exactly go with the periodic trends only. There were certain extra exceptions. They do exist. Like ionization energy of in group 3, electron affinity trend in group 17, there's difference. Density trend in alkali metals, all differ. There are certain exceptions, but those exceptions, if they are lessened, we can say the periodic trends, they are present in the periodic table. Yeah. So periodic trends in the properties of the elements. The periodic trends are based on what? They are based on periodic law, which states that if the chemical elements are listed in the increasing order of atomic numbers, many of their properties go through cyclical changes, with elements of similar properties recurring at intervals. At certain intervals, there is repetition in the properties. For example, after arranging the elements in the increasing atomic numbers, many of the physical and chemical properties of lithium, such as its vigorous reactivity with water, they recur in sodium, potassium, and cesium. So we have seen this. Whatever elements come in a particular group, they will have all similar properties, they will have all same properties. We have seen that the periodic recurrence of the elements with similar physical and chemical properties, when the elements are listed in order of increasing atomic number, results directly from the recurrence of similar electronic configuration in the outer shell of the respective atoms. That is, because of the similarity in the valence shell electronic configuration, there is a recurrence in the properties. If the valence shell electronic configuration is changing, the chemical properties also change. That's the reason whatever elements come in a group, they have same valence shell electronic configuration. Therefore, they all exhibit similar chemical properties. But if you see, when you move from left to right in the periodic table, the valence shell electronic configuration is not same. It changes. Since the valence shell electronic configuration changes, there will be difference in the chemical properties. And physical properties, as we have discussed, they show gradation, variation in increasing order or in decreasing order, you can say. So the first periodic trend what we are going to discuss is atomic radius. See, we cannot exactly measure the size of an isolated atom because its outermost electron have a remote chance of being found quite far from the nucleus. So what we say is atomic radius, it is defined as distance from the center of the nucleus to the outermost shell containing electron. Yes, or sometimes what we say, we take a combined atom, we measure the distance from the between the nuclei, we call it as internuclear distance, and we take half of it. The internuclear distance is called bond length, half of it we call it as atomic radius. So how do we define atomic radius? In two ways we can define, because we cannot actually predict the atomic radius. Why we cannot predict the size of the atom? Because we just know that electrons, they are present revolving around the nucleus, and according to Schrodinger's explanation, there is no exact position for the electrons, right? Therefore, they are present in the cloud. So we say that it is the distance from the center of the nucleus to the outermost shell, valence shell. This is one way of defining. Yes. And other way is you have to consider a molecule. You have to consider a molecule. Each one has got its nucleus. Measure the internuclear distance. Internuclear distance. Internuclear distance, it is also having a name called bond length. Yes, so measure the internuclear distance. Let me say this is atom A, this is atom B. So this is, or I can write it, I can write it like this also. Correct? So I will measure the internuclear distance. So this is radius of atom A, radius of atom B. So RA plus RB is the internuclear distance. Take half of it, you will get atomic radius or atomic size. So half the internuclear distance, I can say atomic radius, or the distance from the center of the nucleus to the outermost shell. Atomic radius is always measured in picometers. 1 picometer is equals to 10 raised to minus 12 meters. So small is the atom. Picometers, 10 raised to minus 12 meters. So depending upon whether an element is a metal or a non-metal, three different types of atomic radii are used. Covalent radius is nothing but atomic radius, ionic radius, van der Waals radius, and even we have metallic radius. So what do we mean by covalent radius? Okay, before going to that, atomic radii have been measured for the elements. The units of the atomic radii are picometers, equals to 10 raised to minus 12 meters. An example, the internuclear distance between the two hydrogen atoms in H2 molecule is measured to be 74 picometers. So H2 molecule, when we say, it is two atoms of hydrogen. So internuclear distance, this is 74 picometers. Therefore, what is the atomic radius of hydrogen? 74 by 2, 37 picometers. So this is the atomic radius of hydrogen. This is how we say atomic radii. Yes, see here. So this is the internuclear distance. Half of it becomes the atomic radius. Okay. So, covalent radius. It is equal to half of the distance between the center of nuclei of two atoms held together by purely covalent bond. Yes, held together by purely a covalent bond. So, whenever we speak about covalent nuclear radius, so if these are the two atoms and they are held by a covalent bond. So, this is a covalent bond. Yes, let me say this is atom A, this is also atom A, two atoms, hydrogen just now we had taken, right? So what happens? This is the radius of atom A, this is the radius of another atom A. So what is this? This is distance in AA molecule. Half of it becomes the what? It becomes covalent radius. So it becomes covalent radius. Covalent radius. So if covalent bond is formed between two different elements, if it is two different elements, then AA and AB won't be same, right? If this is A and B, then the distance will be what? It will be RA plus RB. Yes, distance RA plus RB. Or there is a formula if it is two different. So I can write it here. Internuclear distance I am writing. That is equal to RA plus RB minus 0.09 into XA minus XB, where XA and XB are electronegativities of A and B. So when you solve it out, you will get the internuclear distance. Nuclear distance. Half of internuclear distance will be the atomic radius. Yes, atomic radius. That is covalent radius. Next, ionic radius. So what do we mean by ionic radius? It may be defined as effective distance from the nucleus of an ion up to which it has its influence on ionic bond. So when we have ions, we have ionic radius. So till where there is influence of the nuclear charge, till there we take the radius, distance. Van der Waals radius. Atoms of noble gases have van der Waals radius, not any other. Yes. So how do we define van der Waals radius? So see here. Atoms of noble gases, they are not together. They are far away from each other. They are monoatomic gases, right? Monoatomic molecules they are. So how do we define is, it is half the internuclear distance between the adjacent atoms of two neighboring molecules. So if you have two neighboring molecules, this is one molecule of argon, another molecule of argon. This is a molecule. It is monoatomic molecule. Monoatomic molecules. Remember, noble gases have monoatomic molecules. They exist stably, individually. So when you take half the distance between the two neighboring atoms, that becomes the van der Waals radius. Therefore, we say van der Waals radius is very large. Van der Waals radius is very large. It exists mainly in noble gases because noble gases are held together by weak van der Waals forces of attraction. Weak van der Waals forces of attraction. Yes, the van der Waals radius is half of the distance between the center of the nuclei of atoms of noble gases. Next, metallic radius. It is also called as, see, metallic radius is also called as crystal radius. Crystal radius. Metals have crystal structures, so they are also called as crystal radius. Half of the internuclear distance between two adjacent metal ions is called metallic radius. And here you need to remember, out of all these radii, please do remember that the radius of covalent radius is less than metallic radius, and that is less than van der Waals radius. So this is the order. Please do remember this order. Covalent radius is less. Metallic radius is slightly more. Van der Waals radius is very much more. Yes, so covalent radius is least. Therefore, it becomes strong. It becomes strongest. Where radius is less, distance is less, breaking such compounds becomes difficult, right? So the covalent radius is less. So before going to the variation in the atomic radius in the periodic table, let me first discuss something called screening effect, or it is also called shielding effect. Okay, what do we mean by screening or shielding effect? See, when I have an multi-electron atom, so let me say this is nucleus, positive charge. So first shell, say there are electrons. Second shell, third shell, okay, so there are electrons. Let me indicate them differently. So there are electrons here. And there is one electron here. Let me write the electrons like this. Okay. So let me say my outermost shell is having one electron. Okay. And this electron is called what? It is called valence electron. And all the inner electrons, all these inner electrons, or what they are all called? They are called inner core electrons. Inner core electrons. Yes. We know that all the electrons are attracted by the nucleus. Yes. Okay. If you consider a multi-electron atom, a valence electron in a multi-electron atom, it is attracted by the nucleus. Yes. So it is also attracted by the nucleus. All the electrons are attracted by the nucleus. There is force of attraction between the nucleus and the electrons, we say. Apart from that, it is also repelled by inner core electrons. Yes or no? So there is attraction by the nucleus on this valence electron. So this is attraction. And even these electrons, all electrons are negatively charged. So inner electrons will repel it. Understanding? So on individual electron, there is similar attraction from the nucleus. But if you consider valence electron, attraction is same. But along with this attraction, there is repulsion of the inner core electrons also. So the combined effect of these two, the combined effect of this attractive force of the nucleus and repulsion of the inner core electrons, due to which, so due to the combined effect, the valence electron will experience less attraction. It will experience less attraction from the nucleus. Yes or no? Nuclear attraction is not decreasing. I am not saying this attraction is reducing. The attraction which is experienced by this electron is decreasing because the repulsion of the inner core electrons. So valence electron will experience less nuclear attraction. And this reduced nuclear attraction is called shielding effect. Shielding effect. or you can call it as screening effect. So the outermost electron, the inner electrons, they will shield the outermost electron from the nuclear attraction, due to which the valence electrons experience less nuclear attraction. So what do you mean by shielding effect? Due to the inner core electrons, the valence electron experiences less nuclear attraction. This is called screening effect or shielding effect. And this shielding or screening effect, it depends on what? It depends on number of inner core electrons. Yes or no? As the inner core electrons increase, the repulsion increases. Yes. So I can say, what I will say here is, so I'll say here, higher the inner core electrons, higher the inner core electrons, greater shall be the screening effect. Screening effect. And nuclear attraction decreases. Yes, nuclear attraction decreases. And this is called screening effect constant. It is represented by the symbol this. So this represents screening effect constant. So magnitude of screening effect. This magnitude of screening effect, in case of S and P block elements, it increases in a period. In S and P block, it increases in a period as well as in a group as atomic number increases. So as atomic number increases, it also increases. Now, effective nuclear charge. It is based on screening effect only. Effective nuclear charge. It is denoted as ZEFF. Z is nothing but atomic number, that is nuclear charge. So what happens? What did we explain here? Due to due to inner electrons, the valence electron experiences less nuclear attraction. So it experiences less nuclear attraction. It is called screening effect. So this reduced, so due to the screening effect of the valence electron experiences less attraction towards the nucleus, what happens? This brings decrease in what? Nuclear charge actually present on nucleus, correct or no? On that valence electron only. So it brings decrease in the nuclear charge. That decrease in the nuclear charge is called effective nuclear charge. The reduced nuclear charge. So what is effective nuclear charge? The reduced nuclear charge due to what? Due to shielding effect or screening effect. Due to shielding effect or screening effect is termed as effective nuclear charge. It is either denoted like this or it is sometimes denoted as Z star. Yes, therefore I can say Z effective is equal to actual nuclear charge, and it is reduced due to what? Due to screening effect, and screening effect constant. Screening constant. This is the formula. So magnitude of effective nuclear charge, Z effective, that is magnitude of effective nuclear charge, it increases in a period. As you move from left to right, magnitude, please remember this. As you move from left to right in the periodic table, left to right, this is required for our periodic trends now, atomic size variation, all it is required. As you move from left to right in the periodic table, effective nuclear charge increases. Yes, it increases in a period when we move from left to right. Yes. And as you move from top to bottom, it remains almost same. It remains almost same. Understanding? So effective nuclear charge across the period, it increases. It increases. So when effective nuclear charge is increasing means what? The decrease in the nuclear charge is increasing. So electrons will be decreasing. It is held more strongly. The electron is held more strongly. This is all about screening effect or shielding effect. So screening effect or shielding effect means what? In a multi-electron system, the valence electron experiences less nuclear attraction due to repulsion of inner core electrons, and that is called screening effect or shielding effect, and it is constant for particular atoms. Now, because of the screening effect, there is decrease in the nuclear charge actually present on the nucleus. The reduced nuclear charge due to shielding or screening effect is called effective nuclear charge, which is denoted as Z asterisk or Z effective, and that is equal to Z minus the screening constant. As you move from left to right in the periodic table, effective nuclear charge increases. That means it becomes more and more less. There is decrease in the nuclear charge. Yes, it increases. It becomes more and more. Yes, so this is about effective nuclear charge. With this effective nuclear charge, in the next class, in the next video, we will discuss the variation of atomic radius in the periodic table and all the remaining periodic trends. Hope you have followed till here. Please practice all the concepts. Thank you.